Welcome to the first video lecture for the fourth week of the MPP math class. There are only two lectures this week, this one focusing on polynomials, which will be the bulk of the content, and then a second lecture on systems of equations, which will consist primarily of example problems. With polynomials, we talked a little bit about this in class. They're functions that can be expressed in the form you see here. This is perhaps a little too jargony. The second list here is a little simpler. Basically, it's any expression, any function that you can break into the sum of various powers of x with coefficients. Notice that there's no problem if many of the coefficients are 0. We would consider x cubed minus x to be a polynomial even though x squared is not present. We just think that its coefficient would be 0. For polynomials, there are really two ways of talking about the highest power. We can say that the highest power in the polynomial is the degree of the polynomial, or sometimes you'll hear it said the order of the polynomial. So for example, a polynomial that had x cubed, x squared, and x, we would say that it would be a third order polynomial or a third degree polynomial. There are really two skills that you need to develop regarding polynomials. The first is a more straightforward skill involving expanding factors into polynomials, and the second involves solving polynomials or finding the roots for polynomials. When we talk about expanding factors into polynomials, the basic idea is that you have some mixture of terms involving x and maybe some constants all multiplied together that consist of your function. In order to expand this set of factors out, we do something you probably remember from middle school math called the FOIL method. We take the first two terms multiplied together, the outside terms multiplied together, the inside terms multiplied together, and the last terms multiplied together. With any polynomial, after you've gone through this process, you also need to combine like terms or simplify. So in this case, your outside and your inside terms will both be x to the first power, so you can combine those coefficients. If you have a higher order polynomial and factors, there are going to be additional terms in the expression, but the process is basically the same. You need to take each term in the first parentheses and multiply it by each term in the second parentheses. So here we take ax times dx squared, we take ax times ex, and we take ax times f. And then we take, for the second term in the first parentheses, c dx squared, cex, and cf. We then simplify, we combine the x squared terms and we combine the x terms so that we get it in that familiar polynomial form. So now we'll go ahead and look at a few example problems. With all of these example problems, you might consider pausing the video and trying it out on your own. So here we'll start off by multiplying the first terms together first. So we get 4x to the fourth power minus 2x squared. And then we'll do the middle term here, minus x cubed and plus x. And finally, we'll do the last term. We get plus 8x squared minus 8. Next, we put together any common terms. The way that I usually do this is I start with the very highest order. There's only one term here where x is to the fourth, so I put that down. I then look for any x cubed terms. I only have one here, so I'll write that. I then look for any x squared terms. I have 2 I need to combine. I get plus 6x squared. I look for x terms. I have just the 1 plus x. And finally, my constant term. So here we're considering a scenario where you have multiple different factors multiplied together. The easiest approach here is to take it one at a time. So I'm going to start off by multiplying just these first two terms together. So I get x squared minus x plus 2x minus 2. And while we're at it, I may as well multiply together these two terms. So I get x squared minus 3x plus x minus 3. I'm going to combine like terms, so I get x squared plus x minus 2 times x squared minus 2x minus 3. I'm going to go ahead and now distribute across the remaining factors. I get x to the fourth minus, distributing here the first term, x squared, minus 2x cubed minus 3x squared. Now distributing the middle term of the first parentheses, plus x cubed minus 2x squared minus 3x, and finishing up with a constant term, negative 2 minus 2x squared plus 4x plus 6. Final step, I need to combine like terms. I look for my highest order power, it's x to the fourth. I then look for any cubed terms. I have 2 of them. I combine them to get minus x cubed. I look for x squared terms. I have 1, 2, 3 of them. I get minus 7x squared. I look for any x terms. I have 2 plus x. And finally, my constant term plus 6. So you see, by systematically expanding smaller portions of the factorial form, I'm able to expand this polynomial out into its longer polynomial form. The other thing you need to know how to do with polynomials is to find their roots. Roots of a polynomial are the values of x for which the entire polynomial expression is equal to 0. There are quite a few natural scenarios where you need to know the roots of the polynomial. For your lives, the most salient is probably the fact that if you're looking to do something like maximize someone's utility function, the approach that you use is typically to take a derivative and then set the derivative equal to 0 and solve for the variable that's left, which, if you have a derivative that is in polynomial form, entails finding the roots of the polynomial. There are a few other settings that you'll run into where it's useful. For example, in graphing, finding the roots is equivalent to finding the x-intercepts. And if you have a rational function with polynomial on the bottom, the way that you know which values to exclude from the domain is by solving for the roots of the polynomial. The approach to finding roots really depends on what type of polynomial you're looking at. For first-order polynomials, the solution is trivial. It's the equation for a line. You know how to solve for the x-intercept. You set y equal to 0. You solve, you get that x is equal to negative b over a. For second-order polynomials, which are also called quadratics, there are several approaches that you can use. We're going to talk through each of them. You could factor the quadratic. You could recognize the form of the quadratic and understand how to factor it immediately. You could use a process called completing the square, or you could apply the quadratic formula. When you have a higher order polynomial, there are a few approaches to try. Some of them you can sort of see how they factor naturally. There are a few familiar forms that you should memorize, but in practice, anything higher than a quadratic we would typically solve using a computer just for the sake of speed. When it comes to factoring quadratics, your goal is to basically take a polynomial expression like x squared plus cx plus d and rewrite it as the product of two terms, x plus a and x plus b. What you might notice is that when you expand out x plus a times x plus b, you get a consistently you get that the coefficient on the x term is equal to the a plus the b, while your constant term is equal to the a times the b. So what you end up trying to do is trying to find the combination, any combination of values of a and b such that a plus b is equal to your coefficient c and a times b is equal to your constant term d. So we'll do just one quick example of that. In many ways, factoring is sort of a trial and error process. What you want to do is you want to ask yourself if there are two numbers where if you add them together, they'll give you -7, and if you multiply them together, you would get 6. In other words, one thing plus another thing is equal to -7, while that thing times the other thing is equal to 6. If you see this quickly, fantastic. If you don't see it right away, I'd encourage you to practice it, to try to see it with a number of different polynomials. The solution here is -1 plus -6 is equal to 7, while -1 times -6 is equal to +6. And once you've found those terms, what you're doing is basically saying that x minus 6 times x minus 1 is equal to the expression above. You can always double check your work. If you FOIL this out, you get x squared minus 6x minus x, which would give you 7x, plus 6, which is the expression that you started with. The reason to really try this factoring method is that while it is something of trial and error method, with a little practice you can get very, very fast at factoring polynomials in this way, and it is probably faster than most of the other methods. The good news is that once you have factored the quadratic into x plus a times x plus b, it is really very straightforward to solve for the roots, because what you have to recognize is that if x plus a times x plus b is equal to 0, that's the same as saying either, maybe both, but either of those terms has to be 0. So you're going to have a root where x plus a is equal to 0 and another root where x plus b is equal to 0. And you can see that that's a trivial solution. You get x equals -a and x equals -b, and those are your two roots for this polynomial. The next approach is another thing that it takes a little bit of effort up front. You need to memorize a few forms, but once you've memorized it, it gets to be very, very fast. All I can tell you about this approach is to simply memorize these forms. If you have x squared minus a perfect square, that is the product of x minus a times x plus a. If you have a coefficient in front of the x squared, but otherwise it's the same, then you can take that coefficient and spread it across the two x's. If you have x squared plus 2ax plus a squared, then it is the product of x plus a times itself, or x plus a squared. If there's a negative sign in front of the x coefficient, then you have a negative sign in the factor that you're squaring. And those same two forms have a version with a coefficient in front of the x squared as well. Like I said, the goal to this is really to get very fast at factoring polynomials, and the only real approach here is to go ahead and just memorize these forms. The next approach is something called completing the square, and if you went to school in the United States, you probably remember this with some degree of trepidation. I know that I look back at my own middle school algebra, and I don't think I ever understood the point of completing the square. So hopefully we'll try and do a little better here. So again, you have your polynomial, and basically the goal here is to make the first part of the polynomial a perfect square. And the way that you do that is simply by saying, well, I know that the coefficient on x would be a perfect square, or would make this a perfect square if my constant term were b over 2 quantity squared. So what you do is you add and then subtract that same term from both sides of the equation. Now what we're doing is we're setting this equation equal to 0. So what that lets us do is factor out the first half of the equation and recognize that x plus b over 2 squared is going to be equal to, if the entire polynomial is equal to 0, it's going to be equal to the square root of b squared over 4 minus c. And that will give you the two different roots, the positive and the negative square root of b squared over 4 minus c. Let's go ahead and do a little practice with completing the squares at this point. So I'm first going to talk through sort of a conceptual example that clarifies what we're trying to do here. Imagine that you have a polynomial expressed in this form, where you have some term squared at the front, and then you have a constant term, and you're trying to solve for when that expression is equal to 0. For the most part, if you had something like this that wasn't a squared term, you'd have to work pretty hard. But since the first part here is a squared term, what we can do is we can say, well, I know that x minus 5 squared is equal to 3. In other words, I also know that x minus 5 is equal to plus or minus the square root of 3. What that does is it naturally, if we then solve for the x, spawns our two solutions. We get x is equal to 5 plus the square root of 3, or the other root would be x is equal to 5 minus the square root of 3. So if you have something that's in the form that you see up top here, it makes your life much easier. It's a straightforward process to solve for the roots. So how does that concept apply if we have a more standard sort of polynomial function that looks like this? Well, what we can do is we can say, I know that this is supposed to be equal to 0, and so what I'm going to do is try and get the beginning part of the expression with the x squareds and the x's into that squared format. So I know that if I take x squared minus 3x plus, and I need to take this coefficient over 2 squared. So that would be quantity negative 3 over 2 squared. And for simplicity, I leave off the negative sign because it'll wash out in the square. I need to keep my original constant, and I need to keep the equation the same as it was before by subtracting 3 over 2 squared from the entire expression. And with that in mind, this entire expression is still equal to 0. Okay, so what good did that do me? Well, now the first part of the expression is a perfect square. It's equal to x minus 3 over 2 quantity squared. I'm going to move my constant terms over to the other side so that I get that that is equal to 3 over 2 quantity squared minus 8. If you want to, you can take this constant term and express it out. I'm going to say the first term is 9 over 4, and since I'd like to have a common denominator, I'll multiply the 8 by 2 and get 32 fourths, and so I get here negative 23 over 4, which will end up being important in just a moment. So now what I'm going to say is I'm going to say that x minus 3 over 2 is equal to the square root of negative 23 over 4. And at this moment, every bone in your body should be screaming out that that is not a viable option. It doesn't matter whether we took the positive or the negative root, we cannot take the square root of a negative number. And basically what that's saying is you can imagine a parabola that never crosses the x-axis, and that's what we have here. It's a parabola that is simply never going to cross the x-axis. This might be a good time if you want to try completing this square on your own to pause the video So what I'm going to do is I'm going to look at the coefficient on x. I'm going to say x squared minus x, and the coefficient is -1, so I'm going to add -1 squared would be +1, so 1/2 squared minus 5 minus 1/2 squared is going to be still equal to 0. Now these first three terms make a perfect square. I get x minus 1/2 squared is equal to 5 plus 1/4, or just 5 1/4, or if you want to write it this way, 21/4. I can now look at the square root of that number. I can say, well, I know that x minus 1/2 is going to be equal to either the positive or the negative root of 21/4. So I can solve and get my two roots. I can get that x is equal to 1/2 plus the root of 21/4, or x is equal to 1/2 minus the root of 21/4. Is the final approach to finding the roots for a quadratic polynomial. I'm not going to belabor this point too much because it seems as if most students come in with a fairly solid grasp of this. This is just a formula that you get actually by completing the square. You take the generic quadratic of the form ax squared plus bx plus c. If you use completing the square on it, you get this formula, -b plus or minus the square root of b squared minus 4ac over 2a. So I'm not going to worry about doing too many examples. We can do some in class if you're interested. There are some examples to practice with on the practice problems, but this is something most people come in fairly solid, recognizing how to do. The last topic for today is higher degree polynomials. You'll notice that these equations are basically agnostic as to the location of x. Your a's and b's could be more complicated terms like 5x or 3x, or they could just be constant terms. These forms are worth memorizing. They're the only higher order polynomials I'm likely to ask you to find the root for, is polynomials in this particular format. Notice that once you've gotten the polynomial factored into the right-hand form, for the latter two equations, you would then factor a little bit farther to see if you can't find the roots for, use any of the approaches that we've talked about here today to factor the quadratic factor, a squared minus ab plus b squared, or a squared plus ab plus b squared. And with that, the first lecture for this week is over. The second lecture on systems of equations is next.